Multivariable Calculus, Section 12.7, the chain rule. Chain rule. Recall the chain rule for single variable functions. In Newton's notation, we have h of x equal f of g. Then the derivative of h is the derivative of the outside function f of the inside function, and then times the derivative of the inside function, 3 steps. In Leibniz notation, if u is g of y and y is f of x, then du dx equals du dy times dy dx. Notice that du dy is equivalent to f prime of g, and dy dx is equivalent to g prime. The chain rule for a function of 2 variables. Given z equals f of x comma y, and each of those x and y's are actually functions of t, that makes us have a composite. And so the derivative with respect to t of f of g of t comma h of t is the sum of 2 chain rules. So you start with the partial derivative with respect to x and then multiply that by g prime of t, and then you add to that the partial derivative with respect to y and multiply that by the derivative of h of t. Now, Leibniz thinks that's a bit messy. Here's his formula. dz dt equals the partial derivative with respect to x times dx dt plus the partial derivative with respect to y times dy dt. A lot cleaner, I have to admit. Now notice there's a mix here of partial derivatives and explicit derivatives because we have a mix of single variable functions with a 2 variable function. Now Newton has something to say. Show off. Chain rule for a function of 3 variables. Given w equals a function in x, y, and z, and x, y, and z are each single variable functions in t, then in Newton's notation we have 3 terms added together. The partial derivative with respect to x times g1 prime, and then the partial derivative with respect to y times g2 prime, and add on to that the partial derivative with respect to z times g3 prime. In Leibniz notation, same thing, different notation. You have 3 terms to add together. Newton says, now who's messy? Leibniz says, you are. Extended chain rule for a function of 3 variables. In addition to having a function of 3 variables, each of the inner functions could be a function of 2 variables. In that case, we have 2 partial derivatives. One with respect to independent variable u, and one with respect to independent variable v. Notice that u and v are the independent variables. In the previous examples, t was the independent variable. Now notice that here all the derivatives are partial derivatives because all the functions are multivariable. Now what's Leibniz got to say? Yoo-hoo! Where'd you go, Newton? Yes, Newton's notation gets way too messy. Chain rule for a function in n variables, because in math, in calculus, we're not confined to 2 or 3 variables. We can have as many variables as we wish. This is sometimes called a function in Rn, or in n-dimensional space. Given w equal a function of n variables, and each of those n variables is a function of m variables, notice that the individual inner functions can also be multivariable, and that the 2 sizes of these spaces do not have to match. Well then, for each independent variable t, we have a sum of n terms, each one being the partial derivative of w with respect to each of the x's times each of the x's partial derivatives with respect to that particular tk. So we would have m of these partial derivatives. And Leibniz says, have you seen Newton lately? Number 4, w equals a log of u plus v plus z, and u, v, and z are each single variable functions of t as shown. Compute dw dt. So t is the independent variable, and w is a composite. So here's our formula. And so basically we're going to need the derivatives, the partial derivatives with respect to u, v, and z, and then we're going to multiply those by the individual derivatives of the functions u, v, and z with respect to t. Now notice that the partial derivative of w is always going to be 1 over u plus v plus z, and then the numerator is going to be the respective derivative of u, v, or z, and each one of those is going to be 1. So all three of the partial derivatives with respect to u, v, and z will be identical. And then we're going to apply the chain rule to find du dt and dv dt, and then dz dt will just be 2t. So here's the result of that. And then what we want to do next is get everything in terms of t. Notice that u plus v is going to be 1 because cosine squared t plus sine squared t is 1. And then z is just t squared. So all the denominators change into 1 plus t squared. So now we have this result. And notice that the first two terms cancel. Isn't that nice? And so our final answer is just 2t over 1 plus t squared. Number 8, given w equals yz plus xz plus xy, and these three functions for x, y, and z, compute the partial derivative of w with respect to s and the partial derivative of w with respect to t. So now our independent variables are s and t, but not only is w a function of 3 variables, x, y, and z are functions of 2 variables, and so everything in this computation is going to be partial. So here's the formula with different letters that we're going to use. And so for dw ds specifically, we're going to replace u with s, and the rest stays the same. So we're going to treat t as if it were a constant for all 3 of these, and then in the partial derivatives, the first set of partial derivatives, we'll also be treating some variables as constants. So let me just write this out and then we'll talk about it. So partial derivative of w with respect to x is just going to be, if you look back up at w, it's just going to be the coefficients of the x terms, z plus y. And then the derivative of x with respect to, the partial derivative of x with respect to s, if you look at x equals s squared minus t squared, that's going to be 2s. Then moving to the middle term, partial derivative of w with respect to y is just the coefficients of the y terms, which would be the first and last coefficients, x plus z. And then the derivative of the y function with respect to s is also 2s. And then the last term, the partial derivative of w with respect to z are the coefficients of the z terms. And then the derivative of z with respect to s, looking at the very last function, you've got s squared times t squared, but we treat t as if it were a constant. So we just keep the t squared, and then the derivative of s squared is 2s. Now the fun part, we're going to replace z and y and x with their s and t counterparts. And then we are going to multiply that all out. Algebra is fun. A couple things cancel, and then if we collect like terms, we get our final answer, which you may factor if you wish. Now we're going to have to compute the second part of the question, the partial derivative of w with respect to t. So the same kind of idea, except we replace the u in our formula with a t this time. And so again, the z and z plus y, the x plus z, and the x plus y parts are the same because we didn't change that. But the partial derivatives with respect to t are not different because we did use s before. So in the first term, negative 2t is the derivative of x with respect to t, and 2t is the derivative of y with respect to t. And then in the last one, z equal s squared t squared. This time, s squared is our constant, and we take the derivative of t squared, which is 2t. And then again, we replace our x, y, and z with their s and t equivalents. We distribute. Algebra, algebra, algebra. A couple things cancel again. A couple other things cancel. This is nicer than the last one. And then we collect our negative 2t cubed to make them negative 4t cubed. And if you wish, you can factor your result. Number 10. Given r equals this function in u, v, and w, and u, v, and w are functions in x and y and z. Oh my, oh my. So we've got r is a function of 3 variables, and so are u, v, and w. And they want us to compute the partial derivatives of r with respect to x, and then y, and then z. So we'll start with the partial derivative of r with respect to x, and it's going to have 3 terms because we have a u, we have a v, and we have a w involved in our r function, each of which is a composite, and our independent variables are x, y, and z this time. Okay, deep breath. We're going to treat y and z as constants because x is the only independent variable being considered as a variable in this partial derivative. Okay, so first we're going to look at the partial derivative of r with respect to u using that first equation. The first term has, for u, the coefficient is vw, and then we've got a minus u squared. That derivative will be 2u, and then the v squared and the w squared will go to 0. Okay, so let's just jump right in. And then the partial derivative of u with respect to x is 0 because there's no x in the u function. Moving to the middle term, the partial derivative of r with respect to v, the first term, the coefficients of v would be uw, and then the u squared goes to 0, and we have minus 2v, and the w squared goes to 0. And then looking at the v function, the derivative with respect to x is a 1. The z goes to 0. And then the last term, partial derivative of r with respect to w, the coefficients with respect to w in the first term are uv, and then the u squared goes to 0, and the v squared goes to 0, and we have minus 2w. And then finally, the partial derivative of w with respect to x is again 1. So now we replace v, w, and u with their x's, y's, and z's. We multiply that out, collect like terms, and there's our final answer. So that was 1/3 of the problem. No, the method is the same. So we're not going to repeat the same type of problem 2 more times. We're going to move on. Number 14, given p equals f of 3 variables, and each of those 3 variables is a function of 2 variables, write the chain rule for the partial derivatives of p with respect to each of the independent variables. So here's our formula, and our independent variables are u and v. Our dependent variables then are x, y, and z. And so we're going to have 2 partial derivatives, one for u and one for v. So for u, we have the partial derivatives of p with respect to x, y, and z times their appropriate partial derivatives of the individual x, y, and z's with respect to u. And then for v, it's exactly the same, except instead of u, we have v in each of the second sets of derivatives for x, y, and z. Now, Halloween was a little while ago, and as you know, some people can wear a disguise, and so P is just another letter for F, and so you could see these answers with F instead of P. Either answer is just fine. Number 24, given x, y, z equals sine of x plus y plus z, compute partial derivative of z with respect to x and with respect to y implicitly. Okay, so for the partial derivative of z with respect to x, we're going to treat y as if it were a constant. We're going to treat z as if it were a function of x and y. So we're going to apply the chain rule to z. So on the left, we use the product rule of the functions xy times z. So we've got xy times the derivative of z plus z times the derivative of xy, and since y is a constant, the derivative of xy is just y. Then on the other side, we take the derivative of the outside cosine, and then we multiply by the derivative of the inside, in which case x is our independent variable, so its derivative is 1. Y is treated as a constant, so it goes to 0, and then we have the partial derivative of z with respect to x. Now in the next step then, we need to, actually we're distributing the cosine of x plus y plus z over the quantity 1 plus partial derivative of z with respect to x. And then we need to get our partial derivatives on one side and any term without a partial derivative on the other side. Then we can factor out our partial derivative and finally divide by the quantity on the right. On the left. Now notice that we have z times y, and so the only difference is going to be that when we take the derivative with respect to y, that quantity is going to be z times x. And so the only thing that changes in our answer is that last term in the numerator, which goes from yz to xz. Therefore, I didn't have to rewrite the whole darn thing. Number 26. Use the method of example 6 on page 954 to compute the partial derivatives of w with respect to x and y given these functions. Well, now this one's a little strange because w is given in terms of two dependent variables, u and v, and also in terms of the two independent variables, x and y. So we have to think of w as a function of four variables, two of which are composite functions in and of themselves. So here's the formula, and I've color-coded it so we can refer to some things later easily. You've got your partial derivatives with respect to u, v, x, and y, each multiplied by the partial derivatives of those variables with respect to x. So notice that the partial derivative of x with respect to x is 1, pretty obviously, and the partial derivative of y with respect to x is 0 because y is an independent variable, so y just by itself doesn't have any x in it, and so it's considered a constant in that case, and the derivative is 0. So we don't have to worry about that fourth term. So let me just write this out, and then we'll talk about the individual parts. Notice that I've color-coded the red and the blue to make it a little bit easier to discuss. So we start out with partial derivative of w with respect to u. And so we bring down the 1/2, subtract 1 from the exponent, and then because we're taking the derivative with respect to u, we just use the coefficient of vxy for the derivative of the inside. Then moving to the red one, we look at the u function, and again it's a square root, so the 1/2 comes down, we subtract 1 from the exponent, and then the derivative of the inside with respect to x is just 1. Then moving to the second term, the derivative of the partial derivative of w with respect to v is similar to what we just did, except that now we're looking at the coefficient of v, which is uxy. And then for the blue one, we're taking the derivative of the v function up there at the top, which also has a square root in it. So the 1/2 comes down, we subtract 1 from the exponent, and then the derivative of the inside with respect to x is again 1. And then finally, the last term, we have the partial derivative of w with respect to x, which is the same sort of deal, except the derivative of the inside then is the coefficient of x, which would be uvy, and then times 1 for the partial derivative of x over itself. Now then what your book wants you to do is simplify that. Notice that uv is x squared minus y squared under the radical, and so everywhere there's a uv in our expression we can substitute the square root of x squared minus y squared, and then also everywhere there's just a u or a v by itself we'll substitute those two square roots. Now to carry out all that algebra and simplify it is really messy, so I'm going to use the hand waving method, which means I'm not really showing you how to do it, but it simplifies to that quantity. Now that's half the problem done halfway because I didn't show all the algebra, And so now they want us to compute the partial derivative of w with respect to y, which would be a very similar task. And so that's not happening in this lesson. Number 30, write an equation for the plane tangent to this surface, x squared plus 2y squared plus 2z squared equals 14 at this particular point. Now recall that the normal from a previous lesson is the partial derivative with respect to x, comma, partial derivative with respect to y, comma, -1. And so all we have to do is compute those partial derivatives at that particular point, which in this case is easy because we've got polynomials. And so fx is just 2x, 2y squared goes to 0, and then the only tricky part is that z is a function of x and y, we assume. And so that term gets a partial derivative. So then we set that equal to 0 because the derivative of 14 is 0. And then we plug in our numbers for x, y, and z, 2, 1, and -2. There is no y to plug in, I noticed. And then when we solve for our partial derivative, we get a half. So then we repeat this process for the partial derivative with respect to y. Notice the x squared term goes to 0, and again 2z squared is treated as a composite, and so we have to multiply by the derivative of the inside, namely partial derivative of z with respect to y this time, and then the 14 goes to 0. And again we plug in, this time for y and z, solve for the partial derivative, and it's a half again. So now recall that the dot product of n with any vector on the plane will be 0 because n is perpendicular to the plane. And so we use a generic point x, y, and z combined with 2, 1, and -2 to create a vector on the plane. And so we're dotting 1 half, -1 with x minus 2, y minus 1, z plus 2. And go ahead and do the dot product. And that's a perfectly fine answer, but you might want to simplify that by multiplying through by 2 and then putting all the constants on the right side of the equation. Number 34, a rectangular box has a square base. Find the rate at which its volume and surface area are changing if the base edge is increasing at 2 centimeters per minute and its height is decreasing at 3 centimeters per minute at the instant when each dimension is 1 meter. And notice that 1 meter is 100 centimeters. You're going to have to either use all centimeters or all meters in your calculations. So here's said box. The volume is x squared times y. The surface area is the top and the bottom, so 2x squared, and then the 4 sides that are x by y. Also note that x and y are functions of time, t for time. And the change in x with respect to t when x and y are 100 centimeters is 2. And the change in y with respect to t when x and y are 100 centimeters is -3 because that's decreasing. And we're talking about the volume point when x is 100, y is 100, and the volume then would be 1,000,000. 100 times 100 times 100. So the partial derivative of v with respect to x, you just take the derivative of the x squared, keep the y, plug the numbers in, and the partial derivative with respect to y is just the coefficient of y, x squared, which evaluated 100 is 10,000. So then we need the overall derivative, and notice that this is not a partial derivative because we're ending up with it in terms of the independent variable t, which is the independent variable of a single variable function. So we're using a different formula from earlier in the lesson. And so then we just plug in the numbers and we get 10,000 centimeters cubed. But if we want to answer in terms of meters, then we have to divide by 100 centimeters cubed. So our final answer is the volume of the box is increasing at the rate of 0.01 meters cubed per minute. Okay, now let's get rid of all that and look at the surface area. The point would be 100, 100, and then if you plug those numbers in for x and y in the area formula, you get 60,000 square centimeters. So the partial derivative with respect to x using the area formula, the 2x squared goes to 4x, and then the coefficient of x in the second term is 4y. Put 100 in for x and y, and you get 800. Partial derivative with respect to y, the 2x squared goes to 0, and then the coefficient of 4xy is 4x. Put 100 in for x, and you get 400. So now we combine those with all the numbers we have, and we get an answer of 400 square centimeters. And again, to answer in meters, we have to divide by 100 squared for area. And our final answer is the surface area of the box is increasing at the rate of 0.04 meters squared per minute. So that brings us to the end of our lesson, and I did find an application of these partial derivatives that we've been studying on the web. This is a formula for the soap film on a wire dipped in soapy water. It's your turn to do the homework.